Hi guys, hope you're having a wonderful day. Today we're going to talk about solubility of ionic substances and then also double replacement reactions. So we're going to start with solubility of ionic substances. So if you have a salt, an ionic substance, it could either be soluble or insoluble. And we have solubility rules. So if you look at the back of your periodic table, where you have your polyatomic ions and your activity series, if you look the bottom here, you will see the solubility rules, and it's divided into two boxes. The first box shows you things that are soluble, and it shows also some exceptions. So for example, any salts that have sodium, potassium, or ammonium are always soluble, no exceptions. Things that have chlorides or bromides or iodides are usually soluble. The exception to that is if it's with silver, mercury, or lead. Fluorides are soluble with these exceptions. Nitrates, chlorates, perchlorates, and acetates are all soluble, no exceptions. Sulfates are soluble with these exceptions that are not soluble. The other box is the opposite. So these are things that are not usually soluble, and this is their exception. And this exception actually applies to all of them. So all of these are usually not soluble, except when they're with ammonium or alkali metal cations. Alkali metal cations are like potassium, sodium, lithium, rubidium, and so on. And here it says slightly soluble. The phrase slightly soluble or sparingly soluble or insoluble, all three of those mean the same thing. It means that very, very, very little of it dissolves. So slightly soluble is the same pretty much as insoluble. So let's use these rules to figure out if these things are soluble or not. So KCl is soluble, and you can tell that because the first rule that we have here says that anything with potassium is soluble. The second rule also says chlorides are soluble with these exceptions. We don't have any of those, so definitely KCl is soluble. The next one is AgCl, and AgCl is insoluble, not soluble. So if we look back at our rules, chlorides are usually soluble except when they're with silver, mercury, or lead. So we have silver chloride here, so that would not be soluble. Let's look at the next one. We have NH4Br. This one is soluble. And let's look at our rules. So the first, not the first rule, the first rule right here, ammonium, things with ammonium are always soluble. Bromides are also soluble with these exceptions, which we don't have here. Next one is copper phosphate, and copper phosphate is insoluble. Let's take a look at our rules and how we got that. So phosphates are right here, which are not soluble. And we don't have ammonium or alkali metals, so it's not an exception, it's just not soluble. Copper phosphate is not soluble. Next one is barium sulfate. So barium sulfate is also insoluble. Now sulfates are normally soluble. Let's take a look at the rules. Sulfates are right here. They're usually soluble except when they're with strontium, barium, or lead. And in this case it is with barium, so that is insoluble. Last one here is iron nitrate. That is soluble. We don't really have any mention of iron in our rules, but we do have that nitrates are always soluble and no exceptions to that. Okay, so we can use our solubility rules to tell whether ionic substances are soluble or not. Let's move on to double replacement reactions and how this relates to double replacement reactions. So we're going to look at MgCl2 plus BbNO3 and this is a double replacement reaction. We know that because we have two compounds. So we're going to do it like we normally do. We're going to take the outer two together, so magnesium ion with nitrate ion. So magnesium is Mg2 plus, nitrate is NO3 minus, and so it's going to be MgNO3 2. And then we're going to put the two middle ones together, so lead and chloride. Lead in this case is Pb2 plus, and then nitrate is NO3 minus. Sorry, chloride, not nitrate, Cl minus. So PbCl2. And it's already balanced. Now this is normally what we would write for our regular equation for double replacement. That's how we learn how to write it. We're just going to add one more thing to this, which is we're going to write down whether these things are soluble or not. Any double replacement reaction happens in water. All ionic substances are solid at room temperature, so it's hard for them to collide and react. And so in order to get a double replacement reaction, you need to dissolve your salts in water. So your reactants are going to be soluble and dissolved in water, and so we're going to write AQ next to them, meaning that they are aqueous. And if you want to check with your solubility rules, you'll find out that those are all there. They are soluble indeed. So AQ means that they are soluble. They are in water. Let's look at magnesium nitrate. Is magnesium nitrate soluble? Well, if you look at your solubility rules, you'll see that anything with nitrates is soluble, and so we're going to write AQ here, meaning that it's dissolved in the water in my solution. PbCl2, if you look at the solubility rules, you'll see that that is insoluble. So chloride is right here. Usually it's soluble, but not with lead. And so that is not soluble. So when you have something that is not soluble in your equation here, you have two options. You can either write S next to it, meaning that it's a solid, it's going to precipitate down, or you can write a down arrow if you prefer. I'm going to go ahead and write a down arrow, meaning that it's a precipitate, it's a solid, it does not dissolve. So this is called the molecular equation. This is the equation we're used to. So the normal equation, balanced, and then just added to it the phases, whether it's soluble, meaning you write aqueous, it's in water, or you write S, or down arrow, meaning that it precipitates, it is not soluble. So next we are going to write our complete ionic equation. And so for the complete ionic equation, basically what we're going to do is we're going to look at whether our substances are soluble or not. And if they're soluble, that means that they are in water, and ionic substances in water have their ions dissociate. So for example, if I have NaCl, NaCl is made up of Na pluses and Cl minuses. As a solid, the Na pluses and the Cl minuses are next to each other in the crystal. When you add water, the water gets in between these ions to dissolve them, and so your Na pluses are separated from your Cl minuses. We call that dissociation. The ions are not associated with each other anymore. They are dissociated. They're separated physically. So if we look at our MgCl2 in our reactants here, this means that we have Mg2 pluses and Cl minuses kind of swimming around in the solution, right? When I take this and dissolve it in water, the water gets in between the ions and separates them like that. The other reactant, the lead nitrate, I have Pb2 pluses and I have NO3 minuses. So these are also kind of swimming around in the solution. So what I'm going to do is I'm going to take these two solutions, these are my two reactants, and I'm going to mix them together. So I'm going to go ahead and erase this right here so that I show that I'm going to mix them together. I'm going to combine them together. Okay, so let's start with our reactants first, and we are going to write the complete ionic equation. So we're going to show what ions these are made up of. So we're going to show these ions right here. So the magnesium chloride is made up of Mg2 pluses and Cl minuses. And I only have one Mg2 plus and two Cl minuses, so I'm going to put a 2 right here. Now you want to put the 2 out here because I have 2 Cl minuses. If I put the 2 as a subscript, that means that I have 2 chlorine atoms bonded together with an overall negative charge, which is not what this looks like. So however many you have, you put that outside as a coefficient. So that's the magnesium chloride, that's this part right here. Next, I'm going to look at the lead nitrate, my other reactant. And so my lead nitrate is made up of Pb2 pluses and NO3 minuses. I only have one lead ion and 2 nitrate ions. So my reactants are basically water with these ions kind of swimming around in the solution. So let's see what happens when you put them together. So if I mix these two solutions, let's say those ions are moving around randomly, right? So let's say my magnesium and my lead ions get close to each other. What's going to happen? Well, they're both positive, so if they get a little bit close to each other, they're going to repel each other and separate again. So nothing's going to happen. What if I take my chloride and my nitrate and get them close to each other? Well, they're both negative, so they're just going to repel each other and then go swimming around again. Nothing's going to happen. What if my magnesium ions and my nitrate ions get close to each other? Well, that's a positive and a negative, so they're going to attract each other and make magnesium nitrate, right? But magnesium nitrate is soluble, meaning that if you put it in water, the water is going to get in between and dissolve it, right? And so if I form magnesium nitrate, the water is going to dissolve it and dissociate the ions back, and they're just going to keep swimming around. So every time they get close together, the water gets in between them again, and they keep going. So nothing really happens. So the magnesium and my nitrate ions just keep swimming around. And so if it is aqueous, if one of your products is aqueous, you also write the ions dissociated. So Mg2 pluses and nitrate, and I have one Mg2 plus and 2 nitrate ions. Okay, what if the lead and the chloride get close to each other? So positive and negative, they're going to attract, they're going to form lead chloride. And what happens? Well, once they form lead chloride is not soluble. So what's going to happen is the lead and the chloride ions are going to clump together. They're attracted to each other. Once they form lead chloride, the water cannot dissolve them because it's insoluble. And so they clump together and they precipitate down as a solid. And so when you have something that is insoluble, you write it down as is. You do not dissociate your ions. So what's going to happen here is I'm going to form PbCl2 as a solid. It's going to precipitate down at the bottom of my beaker or test tube, but my Mg2 pluses and my nitrates are going to just keep swimming around in my solution. And every time they get together, because it's soluble, they're going to separate again. So this right here is called the complete ionic equation. Complete ionic equation. So to write your complete ionic equation, basically you go through everything in your molecular equation. Anything that you see that is aqueous, you show what ions that's made up of. The one that is not soluble, you keep it as is. So then next we're going to write the net ionic equation. And for the net ionic equation, basically you look at your complete ionic equation, the one in red, and you cross out anything that you see that's the same on both sides. So I see magnesium 2 plus, so I'm going to cross this out. 2NO3 minus on this side and 2NO3 minus on this side. So what I'm left with is Pb2 plus 2Cl minus yields Pbcl2. Cl2 precipitate. This is your net ionic equation. So the net ionic equation represents what actually happens in the reaction. So what happens in the reaction is that initially these lead and chloride ions are swimming around in the water. Now, after the reaction, they clump together and they form a precipitate right here. So this is the actual reaction that happened. What you crossed out here, the nitrates and the magnesium, these are called spectator ions. So Mg2 plus and NO3 minuses are spectator ions. What does that mean? If you're a spectator, that means like you're watching, right? So, for example, let's say that you play a sport and you have a game and you don't drive yet. So your parents drive you to the game and then they sit there and watch you. So your parents are not involved in the game. They don't participate in the game, but without them, there would be no game, right? You wouldn't be able to get to your game. So that's what the magnesium and the nitrates are. They are spectators. They're important because they bring the lead and the chloride to the reaction in order to react, but they don't actually participate in the reaction. So initially, the magnesium and the nitrate ions are kind of just swimming around, and then at the end, they're still kind of just swimming around in water. And so they have not really done anything. They have not really participated in a reaction. Okay, let's look at another one. So this one is CS3N plus KNO3. So I know that this is a double replacement reaction because I have two compounds here. So I'm going to change the color. Let's go with blue. So I'm going to put the two outer ones together. So the cesium with the nitrates. So I have CS plus and NO3 minus, so that's going to give me CsNO3. And then my K and my nitrites, so K plus and 3 minus, so K3N. I need to balance this, so I need 3 of these. 3 of these, and that's it. Okay, so this is my molecular equation. Okay, I just need to add one more thing, which is what phases they're in. So I know my reactants are aqueous. My products, CsNO3, if you look at your rules, anything with nitrate is soluble. So that is soluble. That's going to go into the water and dissolve, so also aqueous. K3N, anything with potassium, is also soluble. And so this is also aqueous. When both of your products are aqueous, that means there is no reaction happening. And let's see why. So if we were to try to, and basically when you get this, you can say no reaction, all spectators. Here's why. So if we were to try to write our complete ionic equation, you would get 3 CS plus and N3 minus. Those are the ions for CS3N. For KNO3, we have 3 K pluses and 3 NO3 minuses, plus there. For your products, CsNO3 is soluble, so you're going to also show your ions, so 3 CS plus and 3 NO3 minus. And then your K3N is also soluble, so you're going to also show the ions 3K plus and an N3 minus. So then when we try to write, so that's our complete ionic, right? When we try to write our net ionic, you'll see that this cancels with this cancels with this, this cancels with this, and this cancels with this. No reaction. There is no net ionic equation. All of them are spectators. So once you're at your molecular and you see that they're all both soluble, you can just write no reaction, and then all of them are spectators. Okay, let's try another one. The next one is a special double replacement. Why is it special? Because it's a neutralization. It's not just any double replacement, it's a neutralization. I know that because I have an acid and a base reacting together. So I'm going to do it like I normally do. So I have the two outer ones together, so H plus and OH minus. That's going to make water. And then I have, so I'm going to write H2O. And then I have the two middle ones together, so sodium and sulfate. So sodium is +1, sulfate is SO4 2-, so Na2SO4. I need to balance that, so I need 2 of these and 2 of these, and this is your molecular equation. Now let's assign whether things are soluble or not. So we know that both of these are aqueous. Let's skip water for a second. Sodium sulfate, is this soluble or not? It is soluble. Anything with sodium ion is soluble. So this is aqueous. How about water? Is water aqueous? Is water dissolved in water? Well, no, it's not. Aqueous means that you have a solution, right? A solution where your solvent is water. Well, H2O is not a solution. H2O is a pure substance. It's a compound, right? So we can't really call that aqueous. What can we call it? Well, our options are solid, liquid, gas, aqueous. And so out of these options, it would be liquid, right? So water is a liquid. And we're going to write it down as a liquid. And it's actually covalently bonded. So if you look at all the other ones we've done so far, all the reactants and all the products are ionic, and so we see these ions dissociating when they're soluble. This is covalent, so there are no ions here to dissociate. So let's now write our complete ionic equation. So for the complete ionic equation, H2SO4 is made up of H pluses and SO4 2 minuses. We have 2 H pluses and 1 SO4 2 minus. NaOH is made up of Na plus and OH minus. And because of that 2 of this whole thing, so 2 Na pluses and 2 OH minuses. So those are my reactants, my products. I have water. Again, water is covalent. It's not made up of ions. It is sharing the electrons, no charges. And so I don't have any ions to dissociate here. And so when we see H2O liquid, we just write it as H2O liquid. We do not break it up into the ions because it's not made up of ions. The sodium sulfate is ionic and it is soluble. So we are going to break that out into the ions. So we have Na pluses and SO4 2 minuses. We have 2 Na pluses, but only 1 SO4 2 minus. Okay, so this is your complete ionic. Let's look at the net ionic next. So we'll see if we can cross anything out. I see SO4 2 minus here and here, so I'm going to cross those out. 2 Na pluses and 2 Na pluses here. So what I'm left with is 2H plus 2 OH minus yields 2H2O. And you'll see that all 3 of them have a 2 in front of them, so we can reduce this to H plus OH minus yields H2O liquid. So this is our net ionic equation. That's what actually is happening. So initially, I had all these ions floating around, including the H pluses and the OH minuses were in the form of ions, but now they clump together and actually bond covalently and share electrons and form liquid water, and it's not ionic anymore. My spectators in this case would be whatever I crossed out, so the Na pluses and the SO4 2 minus are spectators, or spectator ions. If you have any acid-base reaction, any neutralization reaction, your net ionic equation is always going to be H plus plus OH minus yields H2O. Try it with any of the acid-base reactions and you see this is always going to be the same net ionic equation. Let's do one last one. Na2S plus AgNO3. I'd like you to stop the video, try it, and then play the video again and watch how I do it. So hopefully you already did it. So let's go through it together. So I'm going to put the two outer ones together to form NaNO3. The two middle ones together to form Ag2S. And it looks like I need a 2 here to balance and a 2 here. This is aqueous. This is aqueous. This is also soluble, so aqueous. This is not aqueous, and so it precipitates down. You can put a down arrow or you can put an S. I'm going to put an S just, so you have both in your notes here. So this is the molecular equation. Next, I'm going to write the complete ionic equation. So for the complete ionic equation, I'm going to show the ions that these are made up of. So this is made up of Na pluses and S2 minus, 2 of these. This one is made up of Ag pluses and NO3 minuses. And because of that 2, that applies to the whole thing. So 2 Ag pluses and 2 NO3 minuses. On the other side, NaNO3 is soluble, so this is made up of Na pluses and NO3 minuses, and that 2 again means the whole thing, so 2 and 2. And then my Ag2 plus, because it's not soluble, I'm going to leave it as is. So I'm going to write it just as Ag2S for the solid there. This is the complete ionic. Next, I'm going to write my net ionic. So I see 2 Na pluses here that I can cross out. I see 2 NO3 minuses that I can cross out. So I end up with 2 Ag plus S2 minus yields Ag2S solid. This is my net ionic equation. And my spectators would be whatever I crossed out, so the Na pluses and the NO3 minuses are my spectator ions. And so this reaction, the silver and the sulfide ions are the ones that reacted. They initially were ions floating around in the water, and now they've clumped together to form a solid, insoluble silver sulfide. All right, hope you guys have a great day.